good morning, everybody, and thank you for that introduction. So my name's Paul Hazell, and I'm going to talk to you this morning about the dynamic behaviour of yarns and fabrics. And what I do really is that I'm the, if I can get this to work. Okay. So I run the Impact Dynamics Laboratory at UNSW, and like many of you, we have sort of lots of equipment. We have gas guns, so we've got a two-stage gas gun from Keynote, all the way from Point Brun. We transported it all the way to Australia, and we've got hoppy bars, and we've got sort of drop towers. We've got some modelling capability as well. So what I want to do is really kind of talk about the question of why examining the dynamic response of yarns and fabrics. And of course, really, the answer to that is fairly obvious, because really, yarns and fabrics are important for ballistic protection. So we're really interested in knowing how these yarns and fabrics behave under high strain rate loading conditions. And we know that fabric protection has been around for a good number of years. So take this guy, for example. This is, you'd be familiar with him. He's Archduke Franz Ferdinand of Austria. And you're probably aware of the story behind him. But he actually owned a protective vest. It was a silk protective vest. Sadly, on the day that he was assassinated, he wasn't wearing that silk protective vest. And arguably, even if he was wearing it, he was shot in the neck, so he probably wouldn't have saved his life. But nevertheless, obviously we know that these protective vests are very important. If we jump through to the 1940s, then we see that we have the advent of these flak jackets, and these flak jackets, I don't know if you're aware, but they were kind of made of nylon, and they sort of encompassed these 2-inch steel plates, which were there to sort of mop up all the frags, the anti-aircraft frags, and they were used obviously extensively by the aircrew. Jump forward to the 1950s, and we're still using nylon, and there's an example there of a nylon fragmentation vest, which apparently stopped nearly 75% of fragments and apparently 25% of projectile impacts. And of course, many of you will be very familiar with Kevlar, and you've worked with Kevlar, developed in the 1970s, invented by Stephanie Kwolek. But more recently, we've been interested in this material, which is ultra-high molecular weight polyethylene. And part of what my group's been interested in doing is exploring the dynamic behavior of this material. But understanding the dynamic response of yarns and fabrics isn't just important for these types of protective materials. It's also important for fibre metal laminates. This is an example of some stuff that we've recently done, where we've been looking at the mechanical response of these fibre metal laminates. This is an aluminium front sheet. You can see for the astute view will realise that this has been impacted by a spherical projectile and caused that level of indentation. And what we've been interested in looking at is the behaviour of this in this case, which is a carbon fibre addition to the rear of the aluminium faceplate. So really, the penetration mechanisms in woven textiles is really important to understand. And the ability to defeat a ballistic velocity projectile depends largely on a couple of things. So it depends largely on the energy absorbing properties of fibre, again, at high strain rates. And that's why we're keen to kind of explore how these materials behave under high strain rates, and indeed the amount of energy involved during that process. So you go back to the 1990s, and a very simple way of looking at this was this metric that was developed by Cunniff. And again, this is kind of a neat little simple model that was used to kind of provide a metric for the behavior of individual yarns and fibers. He developed this kind of ballistic effectiveness metric, and you can see that includes a couple of parameters around the specific energy absorption, basically the area under the stress strain curve, and per unit volume, and of course the wave speed propagation along the yarn. Let's just have a look at some dynamic mechanical tests. And I should say as well that the mini review that you can look at, which has accompanied this talk, is open access, so you should just be able to download it in materials letters. I think it's in the January edition 2024. So feel free to download that. So before I go into specific mechanical tests, I just want to kind of talk a little bit about something that we're interested in, and it is related to the behaviour of the yarn and the mechanical response of the yarn, in the sense that you've got here, this is a shock experiment, and this is some work that we did quite a long time ago, where you have a flyer plate that strikes a structure which is aligned, so we drive the shock along the fibre direction. And so what we're trying to understand is the behaviour of this little precursor wave here. So you can see this is the shock that jumps up to about just over 1.3 gigapascals, measured by the front manganese gauge. And there behind you've got this precursor wave as measured by the stress in this polymethyl methacrylate secondary layer. And so the interesting aspect for us is looking at the way in which that precursor wave develops. We're doing some work now on that around looking at these complex structures here. This is some work that has just been started by one of my PhD students using the Theat gun and looking at the way in which we can assess the effect of the individual layers and the way that results in the development of a precursor wave at the rear of the target. So that's a kind of a little bit of I suppose, a sideshow when we're talking about yarns and fibres. But let's now look at some dynamic tension approaches that have also been used by various people. The first is some work that my colleague did, which was Hongzhu, where he's looking specifically at the dynamic response of a yarn here as loaded by a drop tower. So what you've got here is a very sort of low mass, I suppose, anvil, which has been suspended from this yarn. And there you've got this tup, which impacts it at a given velocity. And from that, you can see the difference in the behavior of the failure of the yarns. And so what Hongzhu showed was specifically, as we know with polymers, don't we, that actually with a low loading rate, what happens is that you tend to get a kind of these kind of meandering fibrils, which look a little bit like how you'd expect to get back from a restaurant to your hotel in Colmar after having a couple of glasses of wine. They're kind of a little bit sort of meandering, and you find that as you increase the strain rate, that kind of those sort of little fibrils sort of disappear, and you end up with these fairly sort of clean looking fractures. So just as if the actual hotel was just opposite the restaurant. Some other approaches that have been used. This is a dynamic tension approach, I think developed by relatively locally. And this uses the conservation of energy approach, it's all based upon this, and I'm going to spell this out because I think the acronym is rather unfortunate. It's the tensile impact test for yarn. And you can see what we have. We have a projectile package which is launched along the gun barrel, and it's brought to rest by these copper rings here. It's important that it's brought to rest, and you'll see why in a moment. And that kind of releases this working mass here, And of course, in all of this, what's very important is the way in which the yarn is connected to the working part in the individual test. And so what we're doing here is looking at the yarn sample given a stimulus in tension, and is based upon this the conservation of energy approach, where you've got the changing energy of the working mass here is based upon this the area under the stress strain curve, where VF here is the volume of the yarn. So it gives you, of course, there's some assumptions that are being made here. We're assuming the shape of the stress strain curve, but that gives you a method for looking at stiffness and energy absorption. Another example, which we think is quite neat, is looking at the testing forces, the forces required to pull out yarns which are loaded in tension. And so this work has been looking specifically at pulling out these yarns and with a given preload that's being applied, you can pull out the yarn sort of in plane or out of plane, obviously. And and there's another example of the same type of approach, this time by using a sort of a linear slide here, which kind of gives the same sort of approach where you apply a stimulus to this linear slide, and that results in the yarn being pulled out. And that means that you can look at the pull-out forces, and it's been shown that the higher pull-out forces correlate with ballistic resistance. And we know this, don't we? That I suppose the more friction that you've got between your yarns, and we'll come on to say a little bit more about that in a moment, then the better the ballistic resistance of the fabric. So results have shown that both the in-plane and out-of-plane peak pull-out forces vary linearly with the pretension applied, and during the yarn pull-out, energy is mainly dissipated through friction. And there's a couple of other comments there. So really, just moving on to looking at some other tests. Some other authors have looked at testing yarns ballistically, and there's an example, I suppose, of what we're expecting to see in this. And when we're testing yarns ballistically, we're trying to, and certainly for a single yarn, which is very challenging, because you try and ballistically load a single yarn, and of course with the variability of gas guns becomes rather challenging. But a few authors have had a go at that. So what we're trying to do here is to simplify the ballistic conditions. So here's an example of a single layer of ultra-high molecular weight polyethylene fabric. And you can see that the projectile's it's a 2D image, so it's a little bit confusing, but you can see that the projectile's just about to leave the rear of the fabric. And as it's doing so, the yarn is a single yarn that's doing all the work, and it's being stretched. It's being held on by that single yarn with all its buddies here. You can see that all the buddies are helping that yarn out as they're trying to kind of hold on to that projectile as it's moving its way through. Now, some early work was done on this in the 1950s, and again, several of you will be very familiar with this. This is the model by Smith, and it kind of captures what the classical thinking behind the way in which yarns are stretched by a ballistic velocity. So what you have here, this is the projectile. Here's this is the yarn, and you have a kind of this tent-like formation that's being produced by the impact, and that sets up a couple of waves which are very important for our understanding of the ballistic resistance of fabrics. First is this transverse wavefront. So the transverse wavefront obviously is, as this triangular shape is kind of expanding, And that's relatively slow compared to, of course, the longitudinal wave that's propagating out. So you're getting a wave of stress that's propagating out of the yarn, and simultaneously as well, you get this particle velocity of inflowing material. Now, what Smith really concluded from his work and his model is that he assumed that all the failure that you would see occurred in pure tension. Now, we know that that's not actually the case, and it depends upon a whole bunch of things, including the fact that when a yarn is subjected to impact, that it is subjected to a multi-stress state, and also things like twist. Twist can affect the way in which the transverse wavefront, for example, expands as the yarn is being loaded. Another neat kind of way of testing that is by using a split Hopkinson pressure bar. You can see that this is a nice setup, I think, from these authors here, Song and Liu, where you've got the striker here, and of course we're all very familiar with split Hopkinson pressure bars, where you've got an incident bar which applies a stimulus to the fiber yarn, as you can see the right there. So really, in all these studies, and again, I'm going to do the lazy thing. I just refer you to the review. Just have a look at that. But lower breaking velocities of the projectile have resulted in yarn breakage compared to what was predicted by Smith. So we know that the pure tension is not valid, and we know that also that a multi-axial stress state is present and a likely contributor to the lower velocity of failure. And fiber twist actually plays a role and has been shown to increase the transverse wave speed. All right, so really my closing minutes, which are rapidly coming upon me, sorry. So we just have a look at some things that we've been doing in the laboratory. I'll jump through this rather quickly, but we've been looking at fabrics, looking at the mechanical response of fabrics, but also the ballistic response of fabrics. We've studied the effect of structure. The effect of structure is very important for a fabric layup, looking at tight weaves, loose weaves. We know that tight weaves perform ballistically better. Folded fabrics perform relatively well, because what you're doing with a folded fabric, of course, is that you are effectively increasing the length of the yarn, and that increases the friction as well. We've looked at the effect of matrix, the matrices for sort of more rigid composites as well, and that's kind of, we've been looking at various types of rigid and flexible resins, and really it shows that it changes the penetration mechanisms. Nothing groundbreaking there, of course. We'd know that that's going to be happening, but what's kind of rather interesting is how it affects the transverse wave speed as the projectile is penetrated. And also we've actually just got a defense grant to look at the use of nanoparticles in composite layup. Look at the effect of thickness, of course, and again, this is lots of people have done stuff like this, but you increase the thickness. Again, it changes the penetration mechanism. And last couple of slides. What you find is that as you increase the thickness, your energy absorption per ply, I suppose the way to look at it, actually reduces. And that kind of makes sense, because what you're looking for is this membrane action as the projectile penetrates. And penultimately, not strictly, but anyway, I'll stop talking in a moment. Looked at the effects of coatings and to increase the inter-yarn friction. Okay, so conclusions. I didn't really talk about it, but gripping methods are really important, and I sort of missed that bit, but we talk about it in the review, so just have a look in the review as well. And we find that yarn pull-out tests correspond with ballistic behaviour, and we cannot assume yarn failure is purely tension. Flexible matrices lead to reduced localized strain and an improved transverse wavefront. And of course, we've looked at the structure, the matrix, the thickness, and coatings all affect mechanical behavior. That's my group. That's what we do. Thank you very much.
Yes, thank you very much. We have time for 1 or 2 questions.
Stephen.
Have you considered firing razor blades for something really sharp?
Oh, no, I'll not yet, but we'll. What do you have any insight as to kind of what would that would tell us?
Well, I only know that one of John Field's students some years ago did that on a single yarn, mostly with ball impact, but they also fired razor blades, but razor blades are carrying in a sapper.
Right, yeah.
Thank you very much for this very interesting talk. I would like to know if you were able to observe delamination during your steel ball impacts.
So to do with the fiber metal laminate tests?
Yeah, in the last slide, for instance, you showed a steel ball impacting a plate. Did you observe the delamination between flies?
If it was a rigid, I can't remember specifically, but if it was a rigid composite, there would have been some delamination for sure. Yeah. So I don't actually, and my kind of device here is kind of. So which one do you mean? This.
Come back again. Yeah. For instance, this one. Yes. There are several flies impacted by the steel ball.
Yeah.
And when the bullet is not perforating or anyway, at the end, when you recover the sample, can you see if there is a delamination in play?
Yeah, there is small amounts of delamination going on in that target. It's not a great deal, not compared to what you see where you've got a kind of rigid composite where everything's been stretched out and is permanently sort of held out, but sort of minor amounts of delamination.
Okay, so you cannot correlate it with the impact energy.
We didn't do that. No,
okay.
No.
Thank you.
Yeah, thank you.
Yes, I think we don't. Well, yeah. Do you have one short one?
Thank you again for the talk. I would like to ask you how you process your plate impact experiment. You mentioned very nice plate impact experiment. What kind of data are you getting from that?
Right, so there's 2 approaches that we use. We use manganese gauges, which kind of give you a stress response. Manganese is a kind of a piezo-resistive alloy, so it doesn't. So it's sensitive to stress, but it's not sensitive to temperature or strain. But we keep everything nice and flat and true. And that gives you kind of a voltage, and we can then correlate that with stress. The other approach we use is PDV, where we just take a direct read of the particle velocity of the free surface. So we're measuring the free surface velocity, and so that's the kind of the 2. For equation of state, yes. So for equation of state, historically the only way that we've measured equation of state is that we've used manganese gauges to develop a US-UP relationship. So you've got your shock velocity, and then from the impedance matching technique, you can develop the particle velocity, knowing the impact velocity.
Okay.
Yeah. Okay.
Thank you again.